Hi, everybody. Thanks a lot for the opportunity to present you my project, which is called the RAM Paradigm, a new protocol for uncovering individual differences in walking to an auditory beat. The ability to move to the beat is widespread in the general population, and we often call that auditory motor synchronization. And it refers to the fact that we can synchronize a movement to the beat of a music. So it can be while playing an instrument, walking, or dancing, for example. In the literature, how can we test auditory motor synchronization? Often with tapping, and it shows significant individual differences. So, for example, we can distinguish good and poor synchronizers. But one of the main limits of tapping is that this is a very voluntary movement, in the sense that we don't spontaneously do that kind of movement outside the lab when it's not instructed to. So we need to find a more ecological model to study spontaneous response to a rhythmic stimulus. And we propose gait as a auditory motor synchronization model, because this is a very automatic and voluntary movement, in the sense that we can manipulate the amount of attention that we allocate to gait. And also we can use auditory stimulus to manipulate gait parameters. And we also see individual differences. So for example, in the rhythmic abilities in perception and production. But also in the spontaneous cadence, so this is the number of steps per time, and in the response to an auditory stimulus. So what we call response in that context is how much or how we manipulate the movement parameters, in that case gait, in reaction to the rhythmicity of an external stimulus. But the problem that we have is that there is no method to target specifically individual differences in gait. So the first objective is to divide and validate a new technology to present auditory stimuli adapted to a participant gait cadence, and it is called TINSI-STEP. And we also propose a protocol to detect individual differences in auditory motor synchronization during a gait task, and it's called the RAM paradigm. The material that we use is first, the method that we designed, TINSI-STEP. It's based on TINSI-TAP that has been developed for tapping, and it uses a sensor, so a FSR, force sensitive resistor, that we can see here, that is placed under the heel of the participant in order to detect the steps in real time. We also compare it to a DELSYS FSR as a gold standard, because this DELSYS FSR has been validated in the past. So we can compare our technology to this one that has been validated. Once we are able to detect the step of the participant in real time, we can implement that kind of paradigm. So the RAM paradigm is divided into 3 phases. During the first phase, the participant is spontaneously walking, so without any stimulus, and they're going at their preferred cadence, or spontaneous cadence. During this phase, we calculate our cadence in real time, and we implement a metronome that is going at the same pace, so perfectly synchronized with the step of the participant. And during the third phase, so the RAM phase, the metronome can either accelerate or decelerate progressively up to 20% change compared to the initial spontaneous cadence, or the metronome can also remain constant, and we see how the participant is reacting to that, so how the cadence is evolving in response to that tempo change. And the instruction is to walk naturally with the metronome, so we don't know what will be natural for them, whether they will be influenced or not by this tempo change. For the validation study, we tested 12 neurotypical young adults aged between 18 and 40 years old, and they had no motor or hearing disorder, and they could be musicians or not. For the analysis, we first wanted to validate TINSI-STEP, so we compared the data from DELSYS and TINSI-STEP and used Blunt and Altman analyses in order to validate the system. Blunt and Altman analyses are often used to validate a system compared to a gold standard, and it relies on the comparison of the variability of both systems. In order to validate the sensitivity of the REM paradigm to individual differences, we first had to categorize responders and non-responders in our sample. And to do so, we had to find a systematic and objective criteria to distinguish responders from non-responders. So when we do blunted analysis, we basically have two main outcomes. The first one is the R squared, which is called the coefficient of determination. And basically we compare Dall's interstep interval and Tinsi-step interstep interval. And we want to evaluate how much of Tinsi-step variance is explained by Dall's data. For the system to be validated, this outcome needs to be above 95, which is the case here for this participant that we display here. And we make sure that this is the case generally for the sample. So this is the distribution for the 12 participants. And as you can see here, the median is above 95 and also the mean. Second outcome is the reproducibility coefficient. So basically we compare the delay between Tinsi-step and the average of Dall's, and we want to make sure that one Tinsi-step data point stay within an interval of 1 standard deviation around the average of Dall's data. In order for the system to be accurate, this coefficient needs to be below 5%, which is definitely the case for this participant, but also for the 12 participants that we tested. And this coefficient basically gives the limit of agreement between both systems. The second goal of our study was to validate the RAMP paradigm. So in order to call someone a responder, we needed to find the proper criteria for the response to be really specific and congruent with the metronome change. So the first criteria that we found is that during the second phase, so when the metronome is constant, we shouldn't see any significant slope for the cadence. So obviously there is a certain variability of the cadence, but we shouldn't see a slope. So we shouldn't see a acceleration or deceleration during this phase, because otherwise that would mean that the cadence is drifting independently of the metronome. The second criteria was concerning the third phase, so the ramp phase. We should see, on the contrary, a significant slope during this phase. So it can be either the deceleration slope or the acceleration slope, or both. In that case, the deceleration slope is significant. And now we want to make sure that both slopes are congruent with the metronome. So this one is going in the same direction of the metronome, which is good, and it's significant. For this one, in that case, that could either be non-significant or significant and going in the same direction as the metronome also. And this is to ensure that we don't call responder someone who is always accelerating no matter what the condition is, or always decelerating, for example. So it has to be congruent with the metronome. Once we did that, we noticed that we still have different response profile. So on the left, this is 2 responders, and on the right, this is a non-responder. So obviously, this one shows a very flat slope, which is expected for a non-responder, and this one, those one are significant slopes. But as we can see here, this one is very strongly responding for both condition, and this one is kind of strongly responding for the deceleration, but not that much for acceleration. So we need to find a way to quantify the response. So this is what we call a response score to evaluate how much the person responded to both changes. And the solution that we find is to measure the area between the slope in yellow here and here to quantify the response. So obviously this area is way bigger for this person than this one, and even more than this one. In that case, the sign is important. That's why I chose two colors to show you that the acceleration line in above or below here. So in that case, the score take the sign into account, and both colors are somehow compensated. So the response score for this participant would be 82.9, and this one 34.8, and this one only 1.7. So we do see a very strong difference between those profiles, even among responders. And to calculate the response score, so this is the area between the slope, as we can see here in yellow, divided by the area between the metronome to have a percentage. To conclude, we did see that TINSYSTEP is precise and accurate to assess cadence in real time compared to a gold standard, and that the REM paradigm is sensitive to individual differences in capturing differences between responders and non-responders and calculating a response score, so quantifying the response among responders. The next step is to investigate the distribution of responders and non-responders in the general population. So basically test more participants and try to explain the individual differences in the REM paradigm based on cognitive, rhythmic, or motor abilities. I would also like to acknowledge the help of my collaborators who helped me to do this project, and also the funding in order to complete this project. And thank you very much for your attention.